result, right? And the point here is, derivatives are about, making a connection between tiny changes to the input and tiny changes to the output. Okay, now 80 of stochastic programs. What does that mean? Well, let's try and write another function, and maybe this function will sample from a Gaussian, okay? So maybe I'll make the mean at 0, but the variance depends on the input to the program, okay? And now you might ask, what does it even mean to differentiate a function like this? I'm using this capital letter X to kind of be suggestive of a random variable. In fact, this is kind of like a family of random variables indexed by this parameter P. And you can ask, what does it even mean to differentiate a function such as this, right? And how do we do it? So, and maybe you might even ask, what would happen if I stuck in a dual number, this thing D, into X? Is there, what should I get? Well, so this is an interesting question. So like, what would happen if I ran X of dual number of 2? We're also interested in the discrete random case, which is even more challenging. So we could imagine X of P, maybe X2 of P, actually being a sample from a Bernoulli random variable. Okay, so this is a coin flip with probability 1 of being heads. So let me just show you samples from these two programs. So like X of, this is our Gaussian, this is our Bernoulli. Why does this always happen? Okay, but it's, all right. So is either true or false? Let's bring these programs back up. Um, and we might also ask, what would happen if I put a dual number into X2 of P, right? So what would we get out? Like, is there a meaningful notion of derivative for these programs? Okay, so hopefully that gives you, a sense of what we care about. So in the deterministic AD setting, our goal is this transformation. And, there's a lot of, you know, compiler work, engineering, some math that, like really goes into figuring out this transform. But in the stochastic case, kind of it's not just about the compiler transform, it's also a kind of a new mathematical problem. Because I hope you can see now that this is sort of, this is a Monte Carlo program. It's something which you sample and you get a different output every time. Okay, so it turns out that the notion of derivative we're interested in is the derivative of statistical quantities of the program. So the user, you could say, your contract could be that the user can write any random program they want. And what you will do is you will compute the derivative of the expectation of that program. Okay. But this might actually be a pretty ambitious transformation to do because the user wrote their program most likely in a Monte Carlo way for a reason, right? It's probably because it's, sampling something which would be intractable to just compute in close form, compute deterministically. So it's kind of ambitious of you to say, hey, I'm going to tell you its derivative just as like a deterministic quantity. So maybe a, more reasonable goal is to kind of stay in Monte Carlo space. So someone gave you a program which you can sample from, and your goal is to make a new program which you can also sample from, but unlike the original program which estimated an expectation, your new program is going to estimate the derivative of the original program's expectation. So I've cut out like all the other math in the slide. So this is probably hopefully the only slide with some math. So that are people comfortable with the goal? This is often this quantity here is often called like a gradient estimator in machine learning. And this is the goal when we want to differentiate a stochastic program. So are people comfortable with that? Or if there are any questions, you could ask now. Okay, great. Okay, what do I want to tell you next? Okay, so and yes, then okay, this is Agility Talk, so we have a Agility package, and we're interested in doing exactly this transform. So we're interested in making an API where you can hand in a random function and a parameter, and we'll give you this, it'll produce this new program. Okay. Yeah, and we're particularly interested in the discrete stochastic case. It turns out in the, blanket statements like this are never fully accurate, but it turns out that in like the case of purely continuous stochasticity, people have solutions that they're generally very happy with. There's solutions, like machine learning is called the reparameterization trick, and it has a long history before that. But people are quite happy with what we can do in the continuous stochastic case. So a really interesting research question is what to do in the discrete stochastic case. All right. And this is important because, it appears a lot in the wild. So like, it appears in like discrete stochastic simulations of chemical reaction networks, agent-based models. We want to differentiate through an MCMC sampler, and it's high energy physics. So we have here a real picture of a particle shower, which also contains discrete randomness. Okay, so what next? Okay, so now I want to describe to you a little bit, just kind of hand-wavily, how to think about this problem for a continuous random variable. So this is exactly the program I wrote down for you at the beginning. And before we concern ourselves with limitingly small changes to the parameter p, why don't we just ask, what happens if I perturb this by a finite amount, right? And what I'm plotting here is the PDF of the program, the PDF of the program. And since I'm perturbing a standard deviation, this Gaussian kind of gets wider, right? So this is what's happening distributionally to the program. How can we, sort of turn this into, an AD formulation? Like we need to, how can we, come up with our that program X tilde? Like, so basically we need to come up with a way of like thinking about this change to the distribution. And maybe you can stare at this and like, how would you come up with a notion of derivative for, distribution that's changing like this? And maybe the most natural thing to do is to kind of take derivatives of the density everywhere, right? Sort of take pointwise derivatives of this program. And sort of, starting with these numbers, kind of come up with a gradient estimate. And that's exactly the idea of this score function estimator, or reinforce, which is really like a workhorse in a lot of machine learning. This is as far as I'll go in telling you what it is, but I mean, it's not that hard. And basically it relies on just looking at the distributional density and just taking derivatives of it, right? Okay. But people find that the reinforced estimator, like the estimators derived based on this idea, like in nearly every case, if you do it naively, if you just use this plain score function estimator, it's very high variance. There are a lot of tricks to kind of reduce the variance. But we might start asking if, this is the right or this is the only perspective on how to differentiate a density like this. All right. And in particular, if we go back to this dual number idea, you might ask if we can actually keep this intuition from before of small change in and small change out, and small change to the value of the program, right? So like if this thing, x of dual number of 2.0 were to give us a number, it would sort of represent a small change to the random value. And is there an estimator that kind of works on that intuition? Turns out there is. And basically, you can say that the other way you could describe this change to the Gaussian is you could associate each point with a derivative, with like a vector, which sort of tells you how the measure is flowing. So it's kind of flowing outwards here. And it turns out probably there's some condition, right, that like the divergence of this vector field or whatever is going to correspond to the derivatives of the density you saw earlier. But basically, each point is now associated with a number telling you and these numbers are now in pointing horizontally, right? They're derivatives in value space. Okay. And this is the idea of this reparameterization trick, which structurally will now give you something like this. You can put a dual number into your random program and get, random derivatives out. And it turns out that this will be exactly your program x tilde of p if you were to extract this number in front of the epsilon. Okay, so that's the reparameterization trick. It's also called the pathwise derivative, has a lot of names. And yeah, people really like it. So actually I should go to this slide first. People really like it. So, differentiating programs using, they sort of, another way people think about it is differentiating programs using the same random numbers. And people really like the pathwise derivative or reparameterization trick estimator when it works. Okay. The problem is that it fails for discrete randomness, which, might not be surprising because if I now look at my, X2 Bernoulli program and I put in, a dual number, 0.6, it says, hey, your probability was 0.6, but maybe it was slightly higher. And it's like, okay, what can I do with that, right? I can't change by a small amount, so I'm still heads. And there's nothing I can do about it. But this is not what we would want. This does not give us, because this program, random Bernoulli of P, it has a useful derivative with respect to P, or its expectation does, but we just can't read it off from these numbers. So there's something going wrong in the proof of unbiasedness for the reparameterization trick, that doesn't quite get things working in the discrete case. So, all right, and I guess I'll try and wrap up in 3-4 minutes. I think you're also running a bit behind, so yeah. But sort of the direction of my research is to kind of say, the pathwise derivative approach is really nice when it works. In the discrete case, we sort of seem to have to throw it away and start from scratch, start with these score function estimators, maybe try and make them better. Can we instead try and save the pathwise derivative trick, try and save this idea and come up with estimators which, because they're motivated by this, might be lower variance. Because okay, one big thing I should say is that this whole problem here, this x tilde of p, there's no unique solution. So this isn't just there's a lot of design space here, and one big figure of merit for your x tilde of p is its variance, right? So that's that's a big part of gradient estimation. There's a massive design space. Okay, so what should happen if I do something like this, right? So so we have a package, StochasticAD.jl, and let's try. Instead, we have these stochastic triples, which kind of look like dual numbers. Okay, they look, they print out the same as a dual number. But if I put this into our Bernoulli of P, okay, that's kind of anticlimactic. Let's try again. Okay, okay, okay. This is the interesting case. So what it's telling you very hand wavily is that you originally got 0. Your coin was originally tails, but it could have been heads with and this jump from tails to heads has a weight. Like kind of fancifully, you can say that rather than there being a tiny change, there's a tiny probability of a small but discrete change. There's sort of, this idea like this is sort of the idea of this like perturbation-based estimator, where you sort of look at, you can sort of look at small changes to the program, which kind of, hopefully you can see how this might extend, the intuition from the reparameterization trick, but we try and push this forward for discrete random programs. Okay. So this is sort of what happened to the discrete case. And we can go back to our original picture of now we're perturbing the distribution of a binomial. And basically what this amounts to doing is basically, if something this is a binomial, so it's supported in the numbers from 0 to 10. If the number 3 is losing measure, you don't want to just say it's losing measure. Okay, let's use the score function estimator. You want to say if you're losing measure, if you're losing probability, someone's gaining probability, and you'd like to say who you're giving probability to. And if you kind of want to consider, you'd rather give probability to someone who's kind of close to you. So you'd rather say that this, I don't know, this is it 0, 1, 2, 3, 4, this 5 that's losing probability is giving probability to the 6 who's close by, and the 6 might be giving it to a 7, and so forth. There's sort of the intuition behind the sort of estimators we use in StochasticAD. And there's a lot of mathematical formalism here. And the point is that for these sorts of objects, we have a formal notion of a stochastic derivative. You can prove a chain rule. And once you have a chain rule, you can still get started with automatic differentiation. And this is sort of how it looks. So I made this picture, and later I saw this, I saw this tweet which says that like your first figure in a paper should never just be like a piece of art. It should show something. It should show like the output of some real code. It shouldn't just be like pure art. But I'd already made the figure, so this is kind of like pure art, kind of illustrating how the method works. So this black is kind of like the original program. Maybe you take a random walk, and then the reparameterization trick kind of would consider like a tiny continuous change to x. Whereas here, again, very hand wavily, we consider an alternative that is ideally kind of close, kind of coupled to the original program, and their difference will kind of yield a derivative estimate. Okay, so now wrapping up now, I could do a code demo of coding a random walk, but I'll leave that as like an open thing depending on how much you value your coffee break. But I'll just skip a bit ahead and say, okay, just a couple works I wanted to highlight. So one big application of ours is to differentiate Metropolis Hastings. So this kind of a neat application, but I can't really say much more about it. And then a couple of works I wanted to highlight is right, Metropolis Hastings has this accept reject step, right? That's discrete. So that's why it becomes a discrete gradient estimation problem. There's this really nice work, ADAV, which sort of takes a PL view to this problem of differentiating expected values. To take a very principled approach to like constructing like a language where you can do this transform and make sure it's provably correct. Whereas our approach is kind of nested in this general purpose language, which has its benefits, but also its sharp edges. And then for high energy physics, what's the relevance of stochastic AD? Well, it turns out that these sorts of branching programs kind of appear everywhere. So actually, Michael and Lucas had a paper recently where they considered particle shower program and had some like promising initial applications of the stochastic AD methodology to differentiate them and therefore like optimize their detectors and so forth. And then I think Jerry just had a PR to our package, which I need to review, where he adds like a random scattering example, which stochastic AD can differentiate. And like, I guess the value of stochastic AD is sort of the value of automatic differentiation in general. It kind of decouples this problem of just, write down your program. You can think about, just only have in mind the complexity of writing down your simulator and don't have to worry at the same time in your head about writing this like parallel program which differentiates it. It's sort of the methodology of the transform is kind of decoupled from writing the primal. That's actually a really nice perspective shift. And so with stochastic AD, you can hopefully start writing some discrete random constructs. Maybe we won't handle them. Like there's some that there's a lot that we don't handle. It's ongoing work. But you can write it and ask stochastic AD to differentiate it. Maybe it'll work. Maybe it won't work, but that'll be an interesting research problem, which would, if you solve it, would not just apply to your program, but lots of programs. Okay, so these are, I guess, the main two papers out of this line of work so far. There's this original paper which kind of describes the methodology that I hand waved, and recently we've been working on taking the derivative of Metropolis Hastings. There's code, and the code demo is random walk. Let's say you start at 0, you take 100 steps. Each step you could go, maybe you go right or you stay where you are. So let's add a Bernoulli. Let's make the probability, I don't know, something that's hopefully reasonable. It depends on your parameter. It depends on it depends on your parameter. It should also depend on where you are. So maybe like x plus p over 100, x plus p over 200. Let's return x. Whoops. See if I can actually sample from this. Okay, it's a random program, and now we can take the derivative. You can get a derivative estimate. So this is a random program. It has some expectation, and it's a family of random variables dependent on some parameter p. We can say we can get a new program which computes derivative estimate. We can take its mean for for a number of samples, and just like that, you've written the Monte Carlo program just like 5 lines, and pretty soon after you have the derivative of expectation. So that's what stochastic AD could do for you. And if this was a program like a particle shower, this becomes kind of appealing. Yeah. All right, I'll stop there. Thank you.